So welcome again in the VLSI technology lecture. So in the last lecture, we have already discussed about the basic photolithography process, which is a very important process as far as the IC fabrication is concerned. So now we have to discuss about the our next process while IC fabrication. So after photolithography, as we know that the basic or the essential reason behind the photolithography process is to open a particular window, selective window we need to open. And after that, we have to go for a process which is known as doping process. Okay. So basically what we know about our silicon or any elemental semiconductor or any compound semiconductor is that its conductivity is not enough. Okay, so to enhance its conductivity so that a particular device or circuit can be fabricated out of the made devices, okay, we need to go for the doping process so that its conductivity can be modulated as per the requirement. So our today's topic is basically our doping, how to dope this particular ICs, or you can say the wafers which are uh, got exposed through a UV rays, and we have already opened a particular windows in a region where we want to do the doping process. Okay, so just let's begin the discussion. So in the doping, basically, as I said, we need to add a certain type of dopants to improve the conductivity of our elemental semiconductor or gallium arsenide, which is your compound semiconductor. Okay, so whether it is an elemental semiconductor or a compound semiconductor, basically doping means we have to add a certain type of dopants. As you must be aware about the n-type doping or p-type doping, in which you must be knowing that in the n-type dopant we are having, like for the silicon, we are having arsenic, we are having phosphorus, we are having antimony. These are the n-type popular dopants, and these dopants will be giving you an extra electron in the conduction band so that its conductivity can be enhanced. Similarly, we can also add a certain type of p-type dopants like boron, which is a very popular dopant that can also be used for increasing the number of holes in the our elemental semiconductors. Fine. So this way we can perform the doping to enhance the its conductivity of the semiconductor. So basically its electrical properties is going to be modified by doing the doping. So how this doping is actually performed? So basically there are two techniques which are most popular, like diffusion, and another one is our ion implantation. Okay. So as we can see in this process and in this particular lecture, we will be basically focused upon the diffusion process. Okay. In the subsequent lectures, I will be discussing about the ion implantation. So today's our main talk is based on the diffusion. Okay, so how this doping can be performed with the help of diffusion process. So one thing that you have to remember is this diffusion process is mainly used to form a deep junctions. Okay, it is actually used for deep junctions, and this is our high temperature process. Okay, this is very important 2 points that you have to remember. Similarly, you can see in the ion implantation. This is basically used for the shallow junctions, and this is having a low temperature process. Here I have shown you a very typical profile. Okay, here you can see it is on the concentration of our dopant material when we dope this particular silicon wafer after doing the photolithography and opening the window. When we go for the doping process using the diffusion technique, then this type of profile of doping profile, you can say, you can obtain. So what is this? It is nothing but your concentration of material, okay, which is taken onto the logarithmic scale. Okay, so how it is varying as we go deep inside your material. Okay, so in this way its profile will be changing. Similarly, you can see in the ion implantation, the profile is something like this. Okay, the peak will be somewhere here, right? So in this case, you can see the peak is at the top, okay, at the surface, and then when we go inside the material, this dopant concentration will gradually decreases. Fine. But here the case is different. Okay, here you can see that the at a certain depth you will find the maximum value of the dopant concentration. Okay, dopant concentration will be maximum at a certain depth, and as you go up or go down, its dopant concentration is going to be reduced. So basically we have to look at the process diffusion. Okay, how this diffusion is performed and what is this diffusion, how this means materials or the impurities can be incorporated into a silicon substrate by following a diffusion process. So basically we have to look at the one important thing about this diffusion process is uh, when we, as I explained you in the previous slide about the concentration, doping concentration or doping profile, when we following the diffusion process, you can see that this is another picture. Okay, you can see it is another picture. So you can see that basically whether it is a uh, p type or n type dopant, basically what happens is generally we take a wafer which is either of a p type substrate or it is a n type substrate. So let's say if it is having a p type substrate and we are going for an n type dopant, then this is the profile that you can see. So here you can see this is the uh, depth that we are measuring in the microns. Okay, so here you can see, so this side is actually your top surface. Okay, this is our top surface. So this one is showing you zero point 0.0 means it is the top surface, and here you can see that when we go for the diffusion process for doping, then you can find that the concentration will be maximum at the surface. Okay, and after that as you go deep inside your wafer, okay, then this particular concentration is going to be reduced. It will reduce, it will follow a certain doping profile. We will be look at what doping profile it is exactly following. So we have to see its mathematical uh, equations. Okay, what equation it is going to follow. Then what we can see that at a particular point in the material, okay, at a particular distance from the top, okay, it will keep on diffusing this all impurity atoms, and there will be a certain point at which what we can see is the impurity concentration in the bulk in our substrate. Okay, that impurity concentration of your substrate is going to become equal to the doping concentration of the impurity, okay, at a certain point. So when this happens, the place where this happens, there will be a formation of the junction. Okay, as we know that when we have a p type and the n type semiconductor, then there will be a formation of the junction. Okay, and just both sides of the junction there will be a certain depletion layer. Okay, so that junction is nothing but where the you can say the substrate impurity concentration and the concentration of the dopant that we are adding, okay, when it becomes equal, that particular certain point is called as the junction. Okay, so here you can see that generally when we do the doping is actually divided into a certain two different parts that I am going to explain you now. So basically this depth is very small. Okay, you just remember that generally we have very thick wafer, and when we are going for the doping process, this depth of the junction, you can say, or you can say the depth of the penetration of your this dopant concentration, dopant material, dopant impurities material, okay, impurity atoms is very small. Okay, it is just about 1% of the total wafer thickness. Okay, it will be of the order of microns, like 1 micron or 2 micron maximum. Okay, so that much will be your depth. So that depth will be not very high. We have to look at how this depth can be made very large, or as per the requirement, or how we can increase the depth of the this diffused region. Okay, that we have to look at. So one more thing that you have to understand what is the physics behind the doping process, as we aware about this particular picture. Okay, so as we know that our silicon, if we take the example of the silicon, as we know that the silicon is having the 4 electrons in the valence shell, and as we know that in the lattice of your silicon, you can see that there will be a regular periodic arrangement of the silicon atoms, and all the atoms will be connected through a covalent bond. Okay, So one particular silicon atom will be surrounded by four such silicon, and it will be forming a covalent bond. So basically what we do is, if we want to add an n-type dopant, then we have to replace a particular silicon atom through pentavalent impurities. Okay, so once we add one pentavalent impurity, then one of the electron will be not participating in the covalent bond, and that will be available for the conduction in the conduction band. Okay, and that way it is forming a n-type dopant. Similarly, we can also add a p-type dopant. Okay, so what we can see is, while from this picture, one thing which is very much clear is that basically, if you see in this two picture, what happens is, whenever this like arsenic or boron, as they are the dopant materials, whenever this dopant material is actually occupying a substitutional site. Okay, because there should be a silicon. Okay, if we have not added any dopant, then there must be a certain silicon should be present over here. Okay, so basically what happens is, this dopant is going to occupy a substitutional site, which is normally occupied by the silicon atoms. Okay, similarly in this case also, this particular boron is actually occupying the substitutional site. Okay, so whenever, the one thing that you have to understand from this picture is that whenever the impurity atom is occupying a space, substitutional space in the crystal lattice, then it will be electronically active, and it is going to incorporate a certain type of charge carrier. Either it is, if it is an n-type dopant, then it is going to give you extra electron. If it is a p-type dopant, it is going to give you extra holes. Okay, vacancy of electrons. So it is going to give you extra holes. So so this is one of the very important picture to understand the physics behind the diffusion process. Okay, so you have to remember that once the dopant atom or the impurity atoms is going to occupy the substitutional site, then it will be electronically active. Okay, it is electronically active, and it is going to incorporate either one extra electron or extra hole. Now you must be aware that if we look at the different models of your diffusion, okay, different models, how just to explain the diffusion process. Okay, we know that this silicons will be basically, it will be arranged in a regular periodic structure. Okay, its lattice will be having a large number of silicon atoms connected together via a particular covalent bonds. But we can have a certain pictures. Okay, we can have a certain pictures in which we can have the point defects. Okay, so in case of the point defects, what happens is, generally there will be a certain sites that will be available within the crystal lattice, which is actually not being occupied by your silicon atoms, that should be occupied by a silicon atom. Okay, but there may be a certain point defects. Like here we can see that uh, let's assume that at this particular site there should be a particular silicon atom, but because there is a point defect, there is a chances that there will be a certain vacant spaces that may be available in the periodic lattice. Okay, so whenever there is a point defects into our crystal structure, then these point defects are actually acts as a vacant sites. Okay, and normally what happens whenever we are going for a diffusion process, then based on the host material, which is our silicon in this case, so based upon the host material and based upon the availability of our vacant spaces, or you can say if the point defects are more, then the vacant sites will be also more. Fine. So whenever we are having a large number of vacant sites, and depending on what kind of impurity we are adding, you please remember that I am telling you that what kind of impurity we are adding. Okay, so because we are having a large number of different type of p-type dopants and n-type dopants. Okay, So it depends on what kind of dopant we are going to add. Okay, so that dopant actually when it diffuses, it may go to the substitutional site. Okay, the vacant sites. Okay, it may go to the substitutional site and it will occupy that particular site. Okay, so after occupying this site, there may be a like here it can do a direct exchange with the host atoms. Okay, so if we want to move it further, right, if suppose that we are having a certain impurity which is being occupied by the vacancy, or you can say the point defect points. Okay, so it is a substitutional site. Okay, so at this point when we have the impurities, these impurities can make movement through the crystal by having a direct exchange. Okay, what it will do is it will be replacing this particular atoms. It will change the positions. Okay, it will change the positions, and then this impurity can move through this particular substitutional sites. Okay, uh, there is a chances that this there may be a large number of vacancies, and what happens is that the trapped impurity, okay, the trapped impurity at this particular substitutional site can also make the movement by seeing another vacant site its nearby positions. Okay, and this way it can again make the movement. Fine. So either it can do the movement by having a direct exchange. Okay, direct exchange with the host atom, or it can also make the movement by having a vacancy exchange. Okay, if we have any vacancy at the nearby places, then these impurities can make a movement by exchanging their position with the vacancies. So this way your substitutional impurities can make the movement within the crystal. So as I explained you in the previous picture that whenever any impurity is occupying a particular substitutional site, okay, whenever it is occupying a substitutional site, it is going to it is electronically active, and it is going to give you certain amount of charge carriers, whether it is an electron or it may be a hole, depending on the type of dopant that we are going to add. So now we can look at the another picture. Okay, we are looking at the atomistic model of diffusion. So first our model is our substitutional model. So in this model what we are saying is that our impurity atom is actually going to occupy the substitutional site, which is normally occupied by an silicon atom or the host atom. So to have this particular substitutional model, there should be a certain point defects inside the material. If point defects are there, if there are certain vacant sites, then only these atoms can, impurity atoms can go and sit onto the vacant sites. Okay. Now, similarly, we can also have the interstitial spaces. As we know that we are having the silicon atoms, and between the two silicon atoms we are having the interstitial spaces. Okay, so there is no there is no reason why this impurity atoms cannot sit in between the interstitial spaces, because these interstitial spaces are enough that can be occupied by a particular uh, impurity atoms. So our next model is basically you can see the example. Okay, so this type of substitutional model or the substitutional impurities are our phosphorus, arsenic, and antimony. These are our different examples, the examples of our substitutional impurities. Basically, whenever we are adding such type of impurities, it is going to diffuse through the material using this substitutional model. Okay, so now we can see the interstitial model. In the interstitial model, what happens is we are having the silicon crystal lattice. Okay, and we can see that the our atoms, impurity atoms, are actually not occupying any substitutional site. Rather, it is moving through the interstitial spaces. Okay, it is moving through the interstitial spaces. One thing which is very much clear about this picture is if we compare it with the substitutional site, you can see that whenever we are having a impurity atom which is sitting at the substitutional site, whenever it is making a movement, okay, there will be a formation and breaking of the bonds that will take place, okay, because you know that this substitutional site, the atoms which are sitting at the substitutional site, it is making a covalent bond with the nearest uh, host atoms, which is your silicon, okay. So it will be making a certain bonds. So whenever it is making a movement, certain bonds are going to be broken, and then a certain bonds is going to be formed, okay. So what we can see is whenever there is a movement of a substitutional impurity from one substitutional site to another substitutional site, there will be a formation and breaking of the bonds that is going to be taking place. And to break any bond or to form any bond, obviously we require a certain amount of energy, okay. We need a little bit higher energy to conduct this particular process, okay. And generally because of this process, because it's already being bonded with a certain number of silicons, this type of movement is greatly hampered, okay. This movement is not very free. But here you can see, because the impurity atoms which are available at the interstitial sites, it is not forming any bonds, or it is not breaking any bonds whenever it is moving through the interstitial spaces, okay. It doesn't make any bond, or doesn't make any neither there is a formation of the bond, neither it is nor the bonds are going to be break. So there is nothing such things is going to happen as it was happened in the case of substitutional model, okay. And therefore whenever any atoms which are occupying the interstitial spaces, okay, these atoms are actually electronically inactive, okay. It is not going to add any electron or any hole into your material, and hence it is not even going to enhance the conductivity of your uh, elemental semiconductor. So that's why what we are writing is that this atoms makes a very rapid movement through the interstitial spaces, because neither formation nor breaking of the bonds are going to take place. But this type of impurities are not contribute to doping. So basically it is not going to increase the uh, like your conductivity of your elemental semiconductor. And now you can see we can also consider the combination of the two, okay, that we will look at in the next slide. So one more thing that we have to remember is the interstitial dopants are your group 1 and group 8 elements, okay. These are the examples of your interstitials dopants. So whenever we are having a silicon as a host material, and if you add any group 1 material or group 8 material, these all materials are going to diffuse through your silicon with this particular model, interstitial model, okay. It will be moving through the interstitial spaces. Now we can have another method which is generally called as the interstitial C model of diffusion, okay, interstitial C. So just try to understand what is this interstitial C model. So in the interstitial C, generally what happens is in the silicon crystal lattice, what we can find is we can find a host atom is earlier sitting in a particular interstitial site, okay. It will be sitting in an interstitial site whenever uh, dopant, any impurity atoms which is actually have already occupied a particular substitutional site, then these silicon atom which is sitting into a particular self interstitial into a interstitial space, this is actually called as the self interstitial. And what it will do is it will be pushing this particular uh, impurity atom into the interstitial spaces, and then it will occupy the substitutional site. So what you can say is initially the picture was this, in which this impurity atom was actually sitting at the uh, substitutional site, and at the nearby place there was one host atom like silicon, which was actually sitting at the interstitial space. Okay, and this interstitial silicon atom is called as the self interstitial, and it is actually driving this particular process in which this silicon atom will push this particular uh, impurity atom, and then this silicon atom will occupy the actual substitutional site. Okay, it will go to this particular site and it will be pushing this impurity atom to the interstitial spaces, and then this interstitial impurity is now going to make a certain moment. So this type of impurity is our boron. Okay, so boron is actually your interstitial C. It is following the diffusion process like interstitial C model. Okay, this particular model is being followed by the boron. Now, as we have already seen the interstitial and substitutional, we can also have the combination of the two. Okay, so basically this is our kick out of the Frank-Turnbull mechanism. So in which what we can have is, what we can see is we can have a certain impurity which actually initially occupying the our like interstitial space. Okay, so when it is moving through the interstitial spaces, there may be a chance that it may kick out a certain host atom. Okay, and it will like after kicking out the host atom, it may go to your substitutional site and it will push this silicon host silicon atom to an interstitial site, or which is known as the kick out mechanism. Okay, this is called as the kick out mechanism, in which your interstitial impurity is going to kick out the host silicon atom and it will occupying the substitutional site and send your silicon to your interstitial space. Okay, or otherwise what can happen is this interstitial space, interstitial impurity can make a movement through the interstitial space, and then it will keep on moving until they will find a vacant site. Once it is find a vacant site, it is going like this and it will go to the sit here. Okay, so one thing that is very much clear from this picture is that in this cases our impurity is actually it is going to occupy the substitutional site. Okay, and as we know that in the substitutional site its movement is greatly hampered, but basically its movement, or you can see that its movement through the interstitial space is very high. Okay, so it can move very freely through the interstitial site and then interstitial spaces, and then finally it is going to occupy a certain substitutional site. So this particular kick out or Frank Turnbull mechanism, you can say, or it is basically a combination of your interstitial and substitutional diffusion process. So this particular process is actually followed by your copper, nickel, and oxygen, which is your gold. Okay, so these are the different materials which is following this particular mechanism of diffusing. Okay, diffusion through your atoms. So one thing that you remember that in this method and this method interstitial C, basic difference is that here a self interstitial is actually driving this particular process. Okay, self interstitial is required. So in this case, your self interstitial is nothing but your host cell atom, which is sitting at the interstitial site. Okay, and it is kicking out or it is pushing your impurity which are actually sitting at the substitutional site, and therefore it is making the movement. Fine. So this way we are having a different model that is going to explain, or which is actually explaining the diffusion process. So whenever we are adding a certain type of dopant through the diffusion process, how these impurities are actually incorporated, how it enters into your material like silicon, and then how it is getting distributed, and then it is ultimately going to give you a certain number of extra charge carriers. Okay, whether it is electrons or holes. Okay, so it will only incorporate extra electrons or holes once it is occupying the substitutional site. So you remember that. So this way it is actually going to diffuse through the material. So one of them may be followed, or the combination of this models may be followed. As we know that this atomistic processes or movement of the atoms through the material, they're all quantum phenomena. Okay, and to explain exactly what happens is very difficult, but maybe the combination of this or particular process may be followed to have a diffusion process. So after having this idea of the atomistic models of the diffusion, okay, now let's see what we mean to say a diffusion process. As we know that we are saying how this atoms are actually moving, different atoms, okay, a different impurity atoms which is moving through our silicon crystal, okay. So that we have seen a different mechanism we have seen, okay. Now, first of all, now we have to look at what we mean to say a diffusion, okay. So as we know that if you remember about the perfume bottle, okay, you must have studied this particular example in your schools, that whenever we opening a perfume bottle, then the perfume bottle, even if it is kept in a particular place, the surroundings are having its smell, okay. So basically what happens is, because of the diffusion process, okay, the the smell of the that particular perfume is get spread into the room, okay, or the entire area, uh, wherever it is kept, okay. So basically what happens in the case of diffusion, in the diffusion, if you see at the one point in any material, if we talk about at one point, there will be a very high concentration of particular atoms. At the other point, the concentration will be very low. So you can see if we are having a certain material, okay, very a certain material in which at this point very high concentration of a certain atoms, you can say, if it is available at the other points, the concentration is very small, then obviously this atoms is going to diffuse, or it is going to make a movement from high concentration to the low concentration side, okay. It will be making a movement from high concentration to the low concentration side. If you like draw a certain imaginary line over here, okay, if we draw a certain imaginary plane over here, then what we can see is, because if we draw a line like just at this point, then what we can see, there are large number of atoms at this side, left hand side of this line, and there will be a less number of electrons, less number of impurities at the right hand side. So what we can see that whenever if you see at the thermal equilibrium condition, what you can see, the number of atoms which are actually crossing from left to right will be more as the number of atoms which are crossing from right to left, obviously because the number of atoms available at the left hand side is very much larger than the right hand side. So basically what happens, whenever there is a concentration gradient, we can say, okay, whenever we are having a concentration gradient, then obviously there will be a net movement of a atoms towards certain direction, or you can say towards a direction in which the concentration gradient is low, okay. So in this way, our atom is going to diffuse. Okay, it is going to diffuse, and that diffusion generally take place until the concentration gradient vanishes. Okay, it will be uniformly distributed, and after that, it will be no further diffusion can take place. So basically it also depends on the environmental conditions, okay, and it will depend on the, like if we are talking about the diffusion of the dopant materials into the silicon, then it will depending on the temperature also, okay. So that way our diffusion is actually taking place. The diffusion phenomena is actually, as we can see, it is depending on the concentration gradient. So there were one scientist whose name was the Fick. So Fick was given a certain laws depending on the that actually governs the diffusion process, okay. So the fixed first law, if we see, as we can see that what we can see that the diffusion is actually a process, okay, which is depending on the concentration gradient of our material, okay. Any atoms, if we are having, we can see that if the concentration at this point is very much larger than that point, then if there is a concentration gradient that exists, then there will be a net flow of the atoms, okay, towards the low concentration side. So that can be like written as J, where J is actually the dopant flux. Okay, so J can be written as J directly proportional to dou C x comma T upon dou x. Okay, here we are writing dou C x comma T. So here, so once we remove the proportionality constant, we can add one constant. That constant is our diffusivity D or diffusion constant D. Okay, so we can write like J is equals to minus D dou C x comma T upon dou x. So basically we are writing this C as a function of both space and time. Okay, x comma T. Okay, so let us say we are measuring this towards x direction. This particular from left to right, we are measuring this in the x direction. Okay, so this is our x dimension. Fine. So let us say if our concentration is not only changing with respect to the spaces but also with respect to time. Okay, so our concentration generally, if we talk about a concentration within a material, okay, that is not only changing with respect to the spaces. Okay, it also may change because of the time. Okay, if you keep it for a different amount of time, then obviously the concentration gradient at this space and at this space will also change. So that's why we are writing like the concentration is a function of both x comma t. Now what is J? J is nothing but our dopant flux, and this dopant flux we are defined as the number of dopants, okay, crossing per unit area per second. Okay, so if we take one imaginary plane over here, okay, we just assume an imaginary plane. Okay, so if we assume an imaginary plane, then what we can see is due to certain doping concentration gradient, okay, a certain concentration gradient, okay, when it is flowing, then there will be a certain rate by which this dopant atom will be crossing the area. Okay, this particular plane. Okay, a particular plane. So this is our dopant flux. J is the dopant flux and D is our diffusion constant. So normally diffusion constant is measured in area per second, or normally if it is centimeter square per second or meter square per second. Okay, and our C x comma T, as I said, it is the concentration of a dopant. So it will be the number of dopants per unit volume. Okay, how we can calculate the concentration? Concentration will be your number of dopants available in per unit volume. Okay, so that will be our concentration. So now this is our first law of diffusion. Okay, given by the Fick's. Okay, it is Fick's first law of diffusion. Okay, in which our dopant flux is given by this. This negative sign actually means that this flux is flowing towards a low concentration direction. Okay, so now we can see that this Fick's Fick's having its second law, which is actually relating the diffusion process in space and time. Okay, here you can see we have like written this dopant flux. So dopant flux we have written as like dopant crossing per unit area per second. Okay, it is per unit area per second. Okay, now this second law, what it says is, let us suppose that we are having a particular incremental volume. Let us say we are having a certain cross-sectional area at this point, one certain plane, and another plane at this particular point. Okay, let us say these two planes are actually separated by a small distance dx. Okay, and the cross-sectional area of this particular section is A. Okay, so it is having a uniform cross section. So if we consider certain like a specimen of our semiconductor, and then this particular structure if we consider, so let us say at this point, okay, at this point, the flux which are entering to this particular plane, okay, the flux entering to this particular plane, if we are doing a diffusion process, and let us suppose that the number of impurity atoms which are actually entering to this particular plane with its like flux J1. Okay, so what is J1 flux? And J1 is the number of dopant which are crossing this particular plane. Okay, this particular plane per unit time. Okay, and J2 is the flux by which the number of dopants are coming out of this particular plane per unit time. Okay, because these areas are constant. Okay, areas are constant. obviously when J1 is equals to J2, okay, if the incoming flux and the outgoing flux are same, there will be no net accumulation of the dopants within this incremental volume. Okay, because what will be the volume of this particular section? You can see the cross sectional area is equals to A, and this distance is equals to dx. So obviously the incremental volume will be A into dx. Okay, so what I'm saying is, if we consider the two side of this particular volume, okay, then these two planes, then obviously if J1 and J2 are same, then there will be no net accumulation of the charge per unit area within this incremental volume. But what happens if the J2 is less than the J1? Okay, if J1 is more and J2 is less, so what does it mean? The number of dopants which enters into this volume per second is greater than the number of dopants which are coming out of this volume per second, and therefore there will be a net increase of the number of dopants within this particular volume. Fine. So what we can say is, we can write this as, if J2 minus J1 divided by dx, okay, J2 minus J1 divided by dx, then this will be same as the dou J upon dou x. Okay, so what is dou J upon dou x? What we can write is, this is the net change in the your flux. Okay, J2 minus J1, we are writing it as a net change in the flux changes. Okay, so rate of like here we have defined J as a dopant flux, so this is nothing but a change in the flux. Okay, so change in the flux within this incremental volume dou x. Fine. So once we calculate this dou J upon dou x, okay, you must be thinking like it is here it is, we are writing like a normal derivative, okay, that can be written as dj upon dx, but you remember that J is also a function of time. Okay, J is also a function of time. So it is not just like a J is a normal derivative. Okay, it should be a partial derivative because J is also a function of time. So when J2 minus J1, we can write this equation dou J upon dx. Now, if we want to calculate the rate of change of number of impurities within an incremental volume, okay, so what we want to calculate over here is, what is the like the rate by which the number of dopant atom is actually increasing. Okay, by what rate it is going to be increasing within this incremental volume. So let us say that is denoted by dn upon dt. Okay, where n is the number of impurity atoms within this particular volume. Okay, within this particular volume. So how it can be calculated? This can be calculated by having the change in the concentration. Okay, change in the concentration multiplied with the volume. Okay, there should be a net change in the concentration. First of all, what we can calculate is, what is the concentration which is going to change per unit time. Okay, so because we know that the concentration is nothing but the number of atoms per unit volume. Okay, so what is the number of atoms per unit volume per unit time? So what is the change in the concentration multiplied with the volume will give you the number of dopants which is changing per unit time. Fine. So try to convince yourself. So what we can do is to calculate the rate of change of number of impurities within the incremental volume dn upon dt. We have to multiply the volume with rate of change of the concentration. Okay. So once we calculate the rate of change of the concentration, then how to calculate this dou C upon dou X. Okay. So this can be calculated by having this dou C upon dou T. If we want to calculate, this is same as J2 minus J1. Okay. So J2 minus J1, if we calculate, you will be getting this particular dou C upon dou T into dx. Okay. It is same as calculating the J2 minus J1. Okay, so this is nothing but it is going to give you the total number of impurities which is going to change within the volume dt. Sorry, so this is nothing